Now that we've understood superheat and desuperheating, let's look back at our saturation temperature here. Saturation on the condenser side is changing state from a vapor to a liquid rejecting heat. The temperature is going to stay the same until the state is completely changed. Latent heat is going to have a change in state without a change in temperature. So all of this is going to be the same temperature. We're going to hook our pressure gauge up, and that pressure is going to convert to a saturated temperature, or in this case, a condensing temperature, which is still saturation. So whatever temperature this converts to is the temperature of the majority of that outdoor condensing coil. So it's changing state from vapor to liquid, latent heat, rejecting heat, massive amounts of B2 coming out at this point. Now what's important is after I get it from 100% vapor all the way to 100% liquid, it's still going to be warmer than the air temperature. Let's say the air temperature is 100 degrees. Our refrigerant temperature, just throwing a number out, 115 degrees. So the refrigerant is much warmer than the air. Now that it's completely changed into a liquid, it's still at 115 degrees. The air temperature is 100 degrees. The air is cooler than the refrigerant. The heat's going to leave the refrigerant and go to the cooler air. But now that we've completely changed states, now we can have sensible heat transfer. So the temperature of this refrigerant will start to drop. So now that we've desuperheated a refrigerant, then we change it from a vapor back into a liquid. Now this saturation is still going to be very important. Saturation, PSIG converted temperature. Even though I'm getting my pressure reading over here at this point, it still represents what's happening in the midsection of that condensing coil. PSIG converted to temperature. This saturated temperature is going to be warmer than the air temperature. Let's say it's 100 degrees outside. My saturated temperature may be at 115. So heat's going to leave the refrigerant and go to the cooler 100 degree air. But what's interesting is it's at latent heat. Latent heat is a change of state without a change in temperature. So this section of my condensing coil is all going to be the same exact temperature. Here it's going to be a vapor, changing state. Here it's about 50 vapor, 50 liquid, and eventually we get down to it completely being a liquid. But there's massive amounts of heat being rejected because it's latent heat. Now, after it's completely changed into a liquid, that liquid temperature is still going to be at 115 degrees Fahrenheit at 100 degree outdoor air. Just throwing some random numbers to give you an idea. That's still going to have a heat transfer. The difference is now the heat's going to leave the refrigerant and go to the air, but the refrigerant will start to cool off. It will cool off below its saturation point. If it's 115, then it goes to 114, 113, 112, 111, 110. It's actually changing in temperature, and we can measure this, so this is sensible heat. So there's a new vocabulary word that we have to learn and a new definition, and this is subcooling. And subcooling is defined as a sensible heat removed or rejected from a substance below its saturation. Subcooling, the amount of sensible heat rejected from a liquid below its saturation point. So here's my saturation point. I'm still taking heat away from this liquid, so it's now subcooled liquid. It's a subcooling effect. So the very bottom side of this condensing coil is going to be subcooling. So we're going to add this to a refrigeration cycle, subcooling. And we're going to add the word sensible heat because we can measure this. So we're going to put sensible. This is going to be the very bottom few rows of that condensing coil. Subcooling, sensible heat. So there's a formula for subcooling, and that formula is going to be the liquid saturated minus the actual liquid line. It's opposite of superheat. Liquid saturated temperature, PSIG converted temperature, so my saturated temperature minus my line temperature. My line temperature should be below my saturated temperature. That equals a subcooled liquid. Blank degrees Fahrenheit. Red represents high pressure. This also represents the condensing unit, or the condensing coil. So that's our formula for subcooling, and it's very important. We can just write these numbers in. So here, if my saturated temperature was, let's just throw some examples out. Let's say my liquid saturated temperature, PSIG converted temperature, converts to, let's say, 100 degrees Fahrenheit. Maybe it's an 85 degree day. 85 degree air, 100 degrees saturated, heat transfers. So we get our pressure, convert it to a saturated temperature. Then I put my temperature clamp on the actual liquid line, that small line, and we get the temperature of that. Let's say that temperature was 90 degrees Fahrenheit. So 100 degrees minus 90 degrees would leave us with a 10-degree subcooled liquid. That subcooling is very important. It's telling us what's happening out here. Now this line we learned earlier was a liquid line, so we're going to now add more to that. So we're going to add over here a liquid line, but we're going to put warm, because if you're to touch this line, it's going to feel warm to you and your feelings. So we're going to put warm, but this warm line is really going to be a high pressure. It's the red side, high pressure, subcooled liquid. This line is a subcooled liquid line. Now this metering device measures and restricts the flow of a liquid refrigerant. So I have to have liquid refrigerant coming here. I can't have a liquid vapor mixture. I must have liquid refrigerant. So I want to make sure that we always have at least 2 degrees of subcooling at this point so that we have solid liquid coming into this component. So subcooling is represented in a condensing unit. The liquid saturated temperature minus the actual liquid line temperature equals subcooling. Now let's apply subcooling to our daily lives. Here we have water, right? H2O, dihydrogen monoxide. Now we're all familiar with water. At 0 psi gauge, what is the boiling point of water at sea level? And that boiling point is 212 degrees Fahrenheit. So the liquid saturated temperature is 212. That's the point that it changes state. The point it boils, condenses. Now the next thing we need to know is what is the temperature of this water right now. So we're going to put our thermometer in here. Turn the thermometer on, measure the temperature of this. And our temperature is 83 degrees Fahrenheit. So our actual water temperature at this point is 83. So we're going to write over here 83 degrees Fahrenheit. So next thing we're going to do some math. Ooh, scary, scary math. Do it in your head, or don't be afraid to use a calculator. My teacher said, you're never going to have a calculator with you all the time. You need to know how to do long math. Well, guess what? My phone has a calculator. So we're going to put 212 minus 83 comes to 129. So our subcooling is 129. Now, that number still may not mean much to you. Let's think about this. This water is subcooled 129 degrees below its saturation point. This water is subcooled 129 degrees below its boiling point. So can you drink a subcooled liquid? Yes, you can only drink a subcooled liquid. So all liquids that we're going to be seeing for learning purposes, we want them to be subcooled liquids and superheated vapors. So anytime somebody's saying vapor, I want you to be in your head thinking superheated vapor. Somebody talks about a liquid, I want you thinking a subcooled liquid. If you're going to drink anything at all, think about that being a subcooled liquid. So subcooling, the amount of sensible heat rejected below saturation. And what's cool about this is now we have a refrigeration cycle. But before we move on, let's go see this on an actual unit. So if we think about most of this being our saturated temperature, this very bottom section, all these pipes come back together, and this very bottom 2 sections of this condensing coil is going to be subcooling, cooling the refrigerant off below saturation. So this line is really a subcooled liquid line. If we're to touch it, it's going to feel warm, but really it's a high pressure subcooled liquid. So we're going to take our red gauge, our high pressure gauge, and we'll put it on this port, and this gauge is going to tell us the saturation temperature. So really, it converts to a saturated temperature, PSIG converted to temperature. Then we want to take a thermometer, and we're going to measure the temperature of the actual liquid line. This is going to tell us our actual liquid line temperature. So our saturated temperature, PSIG converted temperature, minus our actual liquid line temperature gives us our subcooled liquid.